all of that stuff taken care of? Like, have you ordered your cap and gown? Good. You done your cross-cultural thing? Good. It's zooming toward us, 4.5 weeks or something. No, 4 weeks. 5 weeks with finals. Okay. Oop. Oh. So, yeah, that's not relevant. Yeah, so we're gonna start, we have 2 or 3 slides left from last time that's very relevant to water balance, fluid balance, which is the real topic of the day. And when we stopped last time, we had these different statements, and then we had written something on the board that said except, like a big except statement, or unless. And this is heading into a topic that has to do with hormones that change water balance. So I want to give a little preview of what that is about. So we have 3 different hormones that our bodies can make that together or individually will affect how much water stays in the body, in the blood, versus how much leaves in urine. And all of them start with A, the letter A, which is kind of annoying from a learning standpoint. And one of them is called anti-diuretic hormone. And we're going to have more information about anti-diuretic hormone in the next slide set. But what anti-diuretic hormone does is it is going to allow water to leave the filtrate. So you can write this, we'll keep this over here so the owl can see it better. So one of the things that anti-diuretic hormone does is it's going to allow water to leave the filtrate kind of at the last minute. So normally by the time filtrate gets to the end of the nephron, water is not really moving much anymore. Because these structures at the end of the tubule system are impermeable. They don't let water cross unless you have anti-diuretic hormone. And if you have anti-diuretic hormone, that's going to allow water to move out of the filtrate or the urine back into the blood using some very specific proteins called aquaporins. And we've got here some, have some pictures of aquaporins. Let me fold this down. It says, at the last minute, using aquaporins. And these pictures really help with that concept. So you can think of this picture as the usual situation where we either don't have anti-diuretic hormone or the level is really low. And we've got here a picture of the tubule system. And in the tubules, there is filtrate, which eventually will become urine as it leaves the nephron. If you don't have a lot of anti-diuretic hormone present, the water that is in the filtrate that got in there doing filtration is pretty much going to stay in there and not go back to the blood. So you will have more water staying in the filtrate, staying in the urine, and that produces dilute urine. So if you've got this picture, circle dilute urine. And make a note that if you've got that situation dilute urine. That's going to result in more water leaves the body. We are going to pee out more water than we would if we did have antidiuretic hormone. So if we are making this ADH, antidiuretic hormone, what that does is it provides a way for water to get back out of the filtrate and go back to the blood. So when you see this picture and there are arrows of water leaving the tubule system, it's going back to the blood. It's just not showing the blood part of this. So if we are making higher levels of antidiuretic hormone, we are going to keep more water in the blood so that we make less urine. And that concept is where the name antidiuretic hormone comes from. It comes from the opposite of a diuretic. So what is if you take diuretics, drugs, pills, whatever, what do those do for you? Hopefully you all have not had to do this. A diuretic is a type of drug and it kind of means double urine. So a diuretic will cause you to put more water into the urine and pee it out. And in the past, people have taken diuretics for two major reasons. One is to reduce your blood pressure, and that's a good reason. The other one is to temporarily lose water weight. And these, hopefully, wrestling organizations that are very dependent on, you must be this certain weight. I hope that they kind of ban these things for that purpose. Because you can take these drugs, they're going to cause you to start making more urine. You pull water, you keep water in the urine and don't let it go back to the blood, and you pee out water, and the water leaves your body, and you are losing water weight. So anything that is a diuretic will cause you to urinate more and thus lose water weight. And they would also cause you to have lower blood pressure, which we'll get back to later in this lecture. So an antidiuretic would be the opposite of that. An antidiuretic would cause you to urinate less. You would retain more water in your body, and it would raise your blood pressure. The opposite of all of these diuretic things. So antidiuretic hormone, we make that in certain circumstances, which we'll look at in a few minutes, but what it actually does, it's going to let water leave the filtrate, which is about to be urine, and the water goes back to the blood, and it helps us keep water in the body. And it does that by encouraging these proteins called aquaporins, like water hole, water pore, aquaporin, to go into the walls of the tubule system. And these aquaporins will let water move. We could draw an arrow, like if water is moving this way through this hole, it's moving from the filtrate back toward the blood. That lets water move. So antidiuretic hormone causes us to keep more water in the blood because it encourages our tubule systems to build these aquaporins that let water go back into the blood, and we pee out less water. So this is kind of a complicated type of reasoning. Like, there is water in your body. It can move between the blood and the urine. There are some hormones that change that. And those hormones also change blood pressure, they change water weight, and they change how much you urinate. So that's kind of where we're heading for that topic in the next slide set. Okay, so I'm going to switch now to our water balance slides. And this is not really a new topic. This is a continuation of things that your kidneys do. And as part of this, we're going to watch a review video about how nephrons work. It's a good bridge between nephrons. I have this friend that he's prepping a lecture about, not a lecture, info session for little kids about blood pressure. And what he was wanting was like a GIF or a GIF of a heart beating that he could put in slides. And it's like, do you use anything like that? I'm like, no, I kind of use YouTube. I just go find YouTube videos that are short and good. It's like, what about the ads? I was like, yeah, they're there. Just kind of hit skip as soon as I can. Yeah, you probably wouldn't want ads if you're looking for videos for little kids, because you just never know what the ad is going to be. So for our class, that rate and that volume that he just described, 90 mils per minute per whatever, that's not very important for us. But a lot of the other stuff that he's talking about is a great review of what we have talked about, except he is using F, R, and S instead of the 2-word names. So when he's talking about filtration, it is glomerular filtration. When he's talking about reabsorption, it is the tubular reabsorption, and the same for tubular secretion. So if you see things in here that he's saying, and I have never talked about that, don't worry about it. But a lot of it is like a great review. And this would be also a great review as you're studying later, or as you're getting ready for exam 4. So all putting back good things back into. So remember, anything that is doing tubular secretion, it's going back from the blood into the filtrate, and we're going to be getting rid of that. So that's that kind of final rebalancing step. And I'm not going to play that right now because I want to wait until I have talked about the hormones and you have heard of them before. So this is a great resource. You can get to this by going to the slides, clicking on the link when the slides are full screen, and it will take you to this video. while I am thinking about this, there are 3 YouTube channels or 3 types of sites that I love their teaching videos. And I would recommend them to you, like for the future, when you're in nursing, you're like, oh my gosh, I don't remember this thing. These are my favorites. So this one is an example called Handwritten Tutorials. And I don't know if it's always this guy, but it's someone and they're drawing and they're doing a nice drawing, speeded up, and they're writing notes about it, and they're about this length and they're about this depth, which is great for undergraduate stuff. Or when you get into your graduate program, you're like, I don't remember neuron function and sodium potassium flows. Review videos really help with that. So this is one of my favorite. There's another one called Bozeman Science, and they have more, it's a guy and he makes all types of videos. He has them for physics, chemistry, and they have more like video and color pictures with it. They're great. And then some really good ones are also from a site called Osmosis. That one you have to pay for. I have come close to doing it to provide them as class resources. So this one, it costs some money. When you're in your graduate program, if you need videos like this, I would find that one worth the money. So very good resources of things like this for when you eventually need them. Handwritten tutorials in Bozeman Science are free, but they have commercials. So we're going to, now that we've kind of reviewed that, let's talk about overall in the body water balance, which is very important to good health, having the correct water balance. This is your quiz questions for the day, for today. Should be. And now we look at overall body water balance. So as humans, we are a large percentage of what we are made of, and what our weight comes from is just water. And of all the water in the body, we can describe it in these 2 major compartments, or like, where is it? It is either inside a cell, within the boundaries of a cell plasma membrane, or it is not. And that gives us these 2 big categories. So if the water is inside a cell, we call it intracellular, like inside, intracellular fluid. But if it is not contained within a cell, we call it extracellular fluid. And your book and some of the slides are going to abbreviate those ICF and ECF. And it's about 1/3 outside cells, 2/3 inside cells. Whoops, forgot to get that on there. So all water in the body is either inside a cell or it's not. So we can define those 2 big compartments. And within those compartments, well, really within the extracellular fluid, there are a lot of places that can be divided up into. So this graphic is showing it in a different way. Like, this represents all the water in the body. 63% is inside cells. That's this. The rest of it is outside cells, but we can divide the outside the cells part into different subcategories, let's say. And those are listed in the blue. So we've got plasma. We know what that is. A lot of your extracellular fluid is just blood plasma in the blood. Some of it is lymphatic fluid is some of it. Some of it is just the liquid in between cells that's not really in the blood or the lymph. We call that interstitial fluid. And remember, I have sometimes called that tissue fluid. The interstitial fluid. So those three places we have talked about in these class, there is water and it's moving this way and that way. This category kind of catches a lot of other liquidy places in the body that come basically from AMP1, mostly. And that's called transcellular. So within transcellular fluid, these are places where you would find that. Your cerebrospinal fluid that goes through your brain and spinal cord, that would be transcellular. Synovial fluid in your joints, that would be transcellular. Fluids in your eye, like the different vitreous humors in your eye. Serous fluid between membranes. So like the fluid between the layers of your lungs, that would be transcellular also. So if you add up these fluidy places with plasma and with lymph and with interstitial fluid, that gives you the fluids that are outside cells or extracellular. So having the right water balance is important for two big reasons. And I don't have a slide to say this, but I think it's important to, before we move on. Correct. Having the correct balance of water is going to allow two big important functions for the body. So the first one is to have enough blood volume. So if we don't have enough water, especially in the plasma, we are not going to be able to pump blood all around the body and supply our cells. So maintaining blood volume is one big deal, that we need correct amount of water in the body. And the second one is to maintain the right concentrations of electrolytes / ions in the body, especially these electrolytes: sodium, potassium, calcium, and bicarbonate. Those aren't the only ones, but those are the most important ones. We need to be maintaining those in certain concentrations, and that's kind of dependent on how much water there is that these are dissolved in. So when our body tries to maintain proper water balance, these are the two things that can go majorly wrong with that can lead to immediately adverse health. Like, you're gonna not have enough blood volume to move around your body. You're gonna not have the right ion balance to maintain your nerve and your muscle function. So having the right amount of water to balance this out is incredibly important. Did some water just leave your body? Yes. Not that much. Not that much. So wherever water is in the body, we got these different compartments, yes, but water tends to move between the compartments because water can do osmosis. So this picture is showing, okay, here's places where water can be. And these blue arrows are indicating the way that water tends to move between compartments. So water tends to move between transcellular fluid and interstitial fluid, and it tends to move out of the plasma and into this interstitial fluid and then into the lymph. It tends to diffuse across cell membranes. So water doesn't always just stay in one compartment. It kind of balances and does osmosis throughout the body. But certain things can help make decisions about where the water is going to end up, or how is this regulated. So water movement is controlled, or in some ways regulated, by fluid pressure, hydrostatic pressure. So that's similar to blood pressure. And the other thing that controls how it moves is the osmotic pressure. And remember that these two things come from different places. The hydrostatic pressure comes from fluid pushing against cells, or against cell layers, like in your blood vessels. The osmotic pressure is something else. So osmotic pressure is going to depend on solutes to pull water across a membrane or across cell layers. So you can think of the hydrostatic pressure is kind of coming from a squishing force, which is usually the heart pumping. Osmotic pressure is coming from saltiness or concentration of solutes in a liquid that's making water move by osmosis. So those two forces happen in a lot of places where water moves, like out of the blood, in capillary beds, in the kidneys, and so on. So once water is in the body, it's going to move in between compartments. But most of what really drives water balance in our body has to do with what fluids we put in and what fluids we release to the outside. So the major sources of how water changes in the body are how much do we pee out versus how much do we drink, really, are the two major things. So this is water input or water intake. How do we get new fluids into the body? There are three major ways. We drink it. So if you got this picture, you could write the word drink in this dark blue. Could be drinking a certain amount of fluids. Certain amount of fluids we eat. They come in through the food that we eat if we're eating moist foods. And then there's a little bit of water that we actually make when we do chemical metabolic reactions. That's kind of a minor amount, but it exists. Mostly it's what we eat and what we drink, water coming in. When we let water leave the body, that's also got a few different aspects of how it's divided up. So you call that the output. How does water leave? So most of it usually leaves through urine. We have a large amount of water that leaves when we talk or when we breathe out. And we don't tend to not think about that, but that is a surprisingly large water loss. We hopefully, our feces are leaving with some water to make them soft enough to move. This is assuming you don't have diarrhea. If you have diarrhea, this becomes much greater. And then sweating also can change depending on the day, but we lose water through sweat. So this would be for an average person on a day that is not special and they're not sick and they're not exercising and they're not in the desert or just on an average day. But these can change depending on what situation a person is in, and they kind of make sense what they are. So if we do not have a good balance of water coming in versus water leaving, we are going to have disorders. And some of these disorders you've heard of more than others, but the first one is dehydration. Dehydration. And everybody knows dehydration is when you're not drinking enough water. Yes, that is true. What this is talking about up here is what the actual problem with dehydration is this. So your extracellular fluid, your ECF, is too soluty, which is really not a word. I feel like it should be a word. It's too concentrated. So you don't have enough water to dissolve properly or to balance out properly your sodium and your potassium and your chloride and things like that. And that's what the actual problem is with dehydration. So when you are dehydrated, your kidneys will start to sense that really before you're even aware of it. And your kidneys will start reclaiming more water out of the urine and keeping more water in the blood. So your kidneys will adjust to try to help you. You will make less urine. Your urine will be concentrated and low volume. But as your kidneys are trying to help you with this, if they're not making as much urine, they're probably not doing the best job they can to get wastes out of your body. So dehydration can also lead to wastes accumulating in the blood more than they should. And hopefully, if you start to become dehydrated, that will trigger your thirst centers. And then hopefully you can drink water and restore the liquid component so that you balance out your ions. If that does not happen, you'll have ion imbalances. And the particular ions that are important here are that same set. So we're concerned about sodium, potassium, calcium, bicarbonate are the top four, I guess I would say. So everyone's heard of dehydration. What might be new is like why it's bad. The reason why it's bad is ion imbalances. And we'll look in a few minutes like, well, what does that cause? Literally, why is that bad? There's an opposite problem that's called hypotonic hydration. This is the opposite of dehydration. The exact opposite. It can be called water intoxication, which sounds stupid. It is a thing. And this does not happen as often as dehydration, but it is still a problem when it does happen. This happens particularly when a person is drinking a lot of water really fast, and the water is ingested faster than the kidneys can process. So it requires drinking a lot of water in a very short amount of time. And there are two situations when this tends to happen to people. What's one situation when someone would drink a huge amount of water in a short amount of time? When they're thirsty, super thirsty,
Drinking water.
super thirsty, like
Dehydrated.
super dehydrated, like huge intake of water. I'm talking like 2 gallons in 10 minutes or something like that. Be careful. Like, People that do distance, like distance cardio,
Yeah.
you want to be drinking continually. The other time when this could happen is if wrestlers have cut weight and they have not been drinking water for 3 days, which is so unhealthy. Then water, 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 too much, too fast can also lead to ion imbalances. The other stupid situation when this happens is if people drink a lot of water on a stupid dare or something like that.
My friend though, she's talking.
Don't,
Yeah.
like, don't let your friends do this. It can be super dangerous.
I wasn't there.
It can be super dangerous. Because you've got the opposite problem. So now if you do this, your sodium, your chloride, sorry, we haven't been including chloride, sodium, potassium, calcium, and bicarbonate are too dilute. There's too much water dissolving these, essentially. They're too dilute, and you end up with, again, ion imbalances. So you really have to be drinking water at an extreme rate to have this happen, but it can happen. And what will eventually happen is if people persist with this, they will pass out. And then at that point, if you know why they passed out, what they need is ions. And they need to quickly pee and get the water out, possibly vomit. But salt tablets could help them if you could make them conscious to eat one. It's very dangerous, very dangerous. It does take a huge amount of water quickly to do that. So you've got a picture here that has words hypertonic, isotonic, hypotonic. And all of these words are in comparison to the body's solute level. And we tend to use these words in relation to drinks. That's what this graphic is set up for. So in plasma, we tend to do the comparison to blood plasma. So plasma is about 0.9% solute, and a lot of that is sodium. Some of it's potassium, calcium, and so on. That's about the level of saltiness or soluteness in our body fluids. So if we are drinking a drink that's about that same level of solute, we call it isotonic. If we are drinking plain water that has no solute in it, we call that hypotonic. And if we are drinking something like Coke or summer camp Kool-Aid that they make, like super, they're putting less water in it, that's hypertonic. Hypertonic. So hypotonic drinks and isotonic drinks are going to aid with hydration more than a hypertonic drink. Because if you drink something super salty or super sugary, you are adding in more solute to the body, and it's actually going to kind of make you more thirsty, so you can balance it out. So something like Gatorade is isotonic, water hypotonic. If a person is having hypotonic hydration, they really shouldn't be drinking anything right now. Definitely not water. But they could possibly drink hypertonic stuff to restore the balance. If people are dehydrated, water is probably best, unless they've lost tons of salt through their sweat, and then they might need isotonic. So you might see these words more when you go into exercise physiology, or have experienced this with your own hydration needs before. When my dad was in high school, he was even in middle school, he was like a great athlete. And his school system was so small that like when he was in 7th grade, he got pulled up to do all the high school sports. And in those days, when you played football, there had been a kid that died somewhere of hypotonic hydration, and it was a huge news, and everyone overreacted to that. So he came through high school sports in the days where like, you cannot have any water during practice, and here's a salt tablet. You've been sweating a lot, here's a salt tablet. Take this, it'll help you. And it was kind of an overcorrection to when it became realized like, oh, people could die from having too much water too fast, they overcorrected. And then in the 70s, late 70s, when Gatorade first came out, it just blew everyone away with the concept of it. Like, you could drink this and it's perfect, and it's perfectly going to replace your electrolytes. Oh, wow. And at first, it's like only professional teams could have this Gatorade stuff. Different these days, so many versions. Okay. So our third disorder of water balance is edema. And we've talked about edema a couple times this semester. And edema is different from those other two because edema is having too much water in a certain place. So edema, get the darker marker. Edema is an imbalance of water in a certain compartment. It's not like overall you have too much water in your body, or overall you don't have enough water in your body. The water is accumulating too much in a certain spot. And it tends to be the tissue fluid or the interstitial fluid. And we've got here examples of people that have edema in one hand or one foot and not the other. So this person, what is this? That their right arm, right hand is super swollen compared to the left. If they had a ring on this hand, they should have taken it off. Hope maybe they did. And this person, their left leg and foot is super swelled up compared to the right. They have edema in particular body part. So, this can come from all different types of problems, can cause edema. If you have liver disease, if you have kidney disease, that can cause edema. If you have not enough protein in your diet overall, this one's a little bit different. So if you don't have enough dietary protein, you have not enough plasma proteins, and you're not going to be pulling water back into the blood very well. So you're losing your osmotic pressure coming from your blood proteins, and when water leaks out of the blood with hydrostatic pressure, it doesn't get pulled back in enough. So you end up with fluid accumulating where it should not. The other thing, things that cause this is if you have inflammation all over your body, that can cause edema. And this arrow that I'm drawing is about inflammation. So inflammation, when you have it, it causes more fluid to leak out of the blood in the first place, because those capillaries open up wider and they become more leaky because of inflammation. And then for these people, if you've got edema on one side or one part of the body and the rest is okay, it's not from these things. So these things would cause edema all over the body. These people likely have a lymphatic obstruction at a certain spot that they're not draining fluid out of their arm. They're not draining fluid out of this leg. This leg's okay. So these people have some type of local problem with lymph drainage, or they may have a blood clot. So you could put under here, they may also have a blood clot in a vein. Anytime you've got a patient or somebody you know, or even yourself, that they've got swelling in one part of the body, it needs to be looked at. So they may also have a blood clot in some local vein that causes blood to back up and then fluid is not exchanging properly. Okay, so now we come to the hormones, 3 hormones, and we will continue with this next time. And some of this is also going to come up in the group learning that we do next Wednesday. But we have 3 hormones and they all start with A, and they help control water balance in the body. One of them is antidiuretic hormone. And all of these are controlling something with sodium and water in the kidneys, and that changes the blood pressure. So I think where I want to kind of end today is doing a conceptual drawing of how this stuff works. So we're going to have a drawing here of, here is the bloodstream. Here's the bloodstream. And in the bloodstream, we have sodium, we have water, we have blood cells, sugars, potassium, calcium bicarbonate, all kinds of important things moving through the blood. And over here, parallel to it, we're going to draw something that represents filtrate. So this is really a kidney situation. We've got blood in the blood system, we've got filtrate in the tubule system. And the blood and the tubules are moving alongside each other. And eventually what's in the filtrate will become urine. And your kidneys, with the help of these hormones, can make decisions on, is water going to stay in the blood or is water going to stay in the filtrate? And is sodium going to stay in the blood or is sodium going to stay in the filtrate? So to understand how these hormones work, there's a very important rule or guideline to remember, which is this. When sodium moves, water tends to follow it by osmosis. So that's guideline number 1. Guideline number 2. When water moves one of these, so if water is moving from the blood into the urine, it's not available to the other. I don't love the phrasing of this, but what I mean is any water that leaves the blood and goes into the urine is leaving the body. And thus, water that leaves the body in urine is no longer in the bloodstream. Maybe that's like so basic, but if water leaves the blood and it goes into the urine and we get rid of it by urinating, it's not in the bloodstream anymore. Conversely, if water at the last minute moves out of the urine and goes back into the bloodstream, we are not going to pee that out anymore. And then third big factor that will help with this when we, what day is this? When we come back to this on Monday, is the amount of water in the blood is the blood volume. And a high amount of water is going to give us high blood pressure. So if the more water we're keeping in the blood, the higher our blood pressure would be. Which means, final thing of the day. Anytime you urinate water out of the body, that is generally going to lower your blood pressure. When water leaves your body through urine, it's not in the blood anymore. It has left the blood, thus urinating indirectly decreases your blood pressure. So on Monday, we're going to look at these three hormones. What are they doing with sodium and water and heat and blood? And how do they change the blood pressure? That's where we're heading. They all start with A. Yeah.